Hello, Chemistry 30, and welcome to a lesson that is quite long on Le Chatelier's principle. Essentially what this is how can we manipulate equilibriums in order to get more of what we want, whether that's a reactant or a product. So we can make changes, which we call a stress, and then the equilibrium will shift or change in order to undo what we did with the stress. So anyways, here's the objective. It's to predict qualitatively using Le Chatelier's principle shifts in equilibrium caused by changes in temperature, pressure, volume, concentration, or the addition of a catalyst, and describe how these changes affect equilibrium constants. So here is Le Chatelier's principle. When a chemical system at equilibrium is disturbed by a change in a property, which we call a stress, the system adjusts in a way that opposes the change. We call this the shift. So we have two things. We have what the chemist does, which is the stress, and then we have the equilibrium's response, which is the shift. Okay, so we kind of talk about two things that take place here. Now, our work is going to be, first of all, figuring out for a stress what the shift will be. And then also, if we want a certain shift, so we want more of, let's say, a product, what stresses can we oppose or give the system in order to make that shift happen? So the basic idea behind Le Chatelier is that equilibriums are like a spoiled, bratty child. Whatever you do, or say to do, the child is going to do the opposite. So it's always opposing the thing that you're trying to accomplish. Now we can use this, a little bit of reverse psychology with the equilibrium to get what we want. So whatever you change in a reaction, the equilibrium is going to fight or ruin that change. It's going to oppose it. So we're going to take a look at three different kind of stresses that we can apply to a system. We're going to look at concentration stresses. So we change the concentration of something either up or down. We're going to look at temperature stresses. So we're increasing the temperature of the whole system or decreasing it. We can't change it for one chemical. It's the whole system at a time. And we're going to look at pressure changes, which are a result of changing volume for the reaction vessel. And then we're going to figure out, does the equilibrium shift to the left, which is towards the reactants, or to the right, which is towards the products? So the whole idea of this, the guiding principle and why Le Chatelier happens, is that it's keeping the Kc value the same, except for temperature changes, right? We talked about how temperature changes the Kc. But what we're doing is when we're changing something, when we're adding a stress, the equilibrium shifts in a way that the Kc value will stay relatively the same by the shift that occurs after the stress has happened. So if you think about it, let's say that I have this Kc expression, and just really briefly here, I have a Kc where I have products over reactants, right? That's kind of, let's just say it's, B over A or something, and it's all ones. I know that doesn't happen, but let's pretend for a second. If I were to add a stress of increasing reactants, so I increase the amount of reactants that's in the reaction vessel, what will happen is that the equilibrium will bring down the reactants and up the products as a result by shifting towards the right, and the Kc value will stay the same. So if I add reactant, I'm essentially adding a bunch of denominator here. And then what it will do is it will convert some of that reactant to product by doing the forward reaction, which lowers this and ups this until the Kc value is staying the same. So mathematically, Le Chatelier is just about shifting the amount of chemical we have so that the Kc value stays identical. So we're going to start with temperature first. It's maybe the easiest one to understand. We're looking at endothermic and exothermic reactions, right? Or directions of the equilibrium. So endothermic, as you know from the enthalpy unit, means that I'm absorbing energy. So energy is going in. In other words, it's a reactant for energy. And exothermic, it's a product. And it's important that before you even start looking at Le Chatelier, you write out energy as a term in the reaction as either a reactant or a product, because that will help you to see what's going to happen. So normally I would do this as a demonstration, but I can't do that. So instead, we're just going to talk about what would happen if I have an equilibrium of 2 NO2 gas produces N2O4 gas plus energy, and NO2 is a brown color, so this is my brown NO2, and N2O4 is colorless. So there's a little bit of NO2 in here, but primarily this is my colorless, right, of just N2O4. So if I have lots of NO2, it's going to be more brown, and if I have more of this, it's going to be more colorless. So let's say that I am making the change of adding warm water. So I am heating this up, and again, this is my colorless right here, while this compound is brown. So if I increase temperature, so this is going up because I'm putting it in warm water for the full vessel. What this system is going to do is it's going to try to use up that energy that's been added from the warm water by shifting to the left. By shifting to the left, it's doing the endothermic direction. It's using up the energy that's now available from the hot water and cooling everything down by producing more NO2. So the stress of increasing temperature and then the equilibrium's response of trying to bring it back down again by doing the endothermic direction of the reaction. So if I go to the left, I'm using up energy because it's endothermic. For the reverse reaction, energy is a reactant, so I'm using it up. So what happens if I place a system in a beaker of warm water? It's going to get more brown. And the reason why is it's doing the endothermic direction. So endothermic shift to use up the added energy. So how will things change? Well, NO2 concentration would be going up, so this would be increasing, while N2O4 gas concentration would be decreasing because I'm shifting to the left, so this N2O4 is turning into NO2. So this is going up while this goes down. All right, let's say we shifted it up, and instead of using warm water, we use ice water instead. So now we're going to be cooling it down. So now what's happening is I am decreasing the energy. Okay, so this is going down. So it's going to go in the direction that brings the temperature back up. So it's going to shift to the right to oppose the stress that I made. I brought it down for energy. It shifts to the right to bring the temperature up again. So if I place this in a beaker of ice water, because N2O4 is colorless, it's going to get lighter brown. Okay, so becomes more colorless. Why? Well, because it shifts in exothermic direction. So shifts in exothermic direction to bring temperature back up. Bring T back up. How will the concentration of chemicals change? Well, N2O4 gas is going to increase, and that happens because of the fact that NO2 gas is decreasing. So I am using up NO2 gas, and then N2O4 gas is going up as a result. So temperature summary, essentially, all you figure out is what is happening to energy, right? So if I am decreasing temperature, if I decrease T, it's going to go in the direction that's going to bring temperature back up. So it goes in exothermic direction. So shifts in exothermic direction. And in the same way, if I increase temperature, if temperature goes up, it's going to shift in endothermic direction in an attempt to bring the temperature back down. So it's always just going to do the opposite. All right, so that's temperature. That's what's happening there. I want to quickly talk about this, and this is kind of a little bit of a cheap or bad way of looking at it. But what happens is you first label the stress that's happening, right? So I label, hey, this is going down. And then I draw an arrow, okay, towards that stress, right? So I kind of view this as two different things that are happening. It's either a takeoff or it's a landing. So this is a landing. I'm landing the plane or helicopter, however you want to view it. So it's going to fly across the arrows, fly towards where it's landing. If I take a look at this one, this was a takeoff. It takes off and then it flies across the arrows after that. Another way of thinking about it is in physics, you learn that vectors always add tip to tail. So these two vectors are always going to be tip to tail, as long as you always draw the shift over top of the chemical reaction, you're fine using that cheat. All right, let's take a look at something else. So this is an example. If I want to kind of maximize something in this reaction, so I have 2 NaCl aqueous plus H2SO4 liquid plus energy produces 2 HCl gas and Na2SO4 solid. So the forward direction is endothermic. So if I wanted to make as much as I could of sodium sulfate, so I want to maximize my yield of this, what would I do to the temperature of the solution? And by solution, I mean reaction vessel. All right, so what you would want to do is you'd want to cause a right shift by increasing the energy. So in other words, we want to increase temperature. Okay, now if we change this to ask a different question, so instead you want to produce the maximum yield of sodium chloride, so I want as much as I can of this. What would we do to the temperature of the reaction? So in this case, I want a left shift, because I want to make more sodium chloride by using up HCl and Na2SO4. Well, in that case, what I want to do is I want to lower energy so that the equilibrium shifts to make the energy again, to bring the temperature back up. So here, I would decrease temperature. Last thing, what is the equilibrium expression for this reaction? This goes back to a review of the previous day. So I would have Kc is equal to, and this is already balanced, which is handy, HCl gas. That's going to be to the power of 2. I do not include sodium sulfate because it is a solid. So this is going to be over NaCl aqueous to the power of 2. I also don't include H2SO4 because it is my only liquid present, so I'm not going to include that. All right, what kind of matter can we not change the concentration of and why? Well, we can't change the concentration of solids because, again, they're not included in the Kc expression because they're not uniformly distributed throughout the reaction vessel. So we can't talk about solids in terms of concentration. And then the other thing that we can't change the concentration of and why is liquids when there's only one thing with a liquid state. So if there's only one liquid, then liquid I also cannot change the concentration of because, again, it's not in solution. It doesn't make sense to actually talk about the concentration. But when I talk about aqueous and gases, those are always included, and liquids if there's more than one. All right, so let's consider this equilibrium. I've got H2O liquid plus 3NO2 gas equals 2HNO3 aqueous and NO gas. And if I take a look at this, I can tell it's at equilibrium right now because all of the concentrations are staying constant. So concentrations are constant. Because they're not changing, I know that this is currently at equilibrium on this graph. So now we're going to look at, let's actually use a stress and see how it shifts and how things react. So if I increase the concentration of NO2 gas in the system, and now we're getting into concentration stresses, and I actually feel like these slides might be slightly out of order, but we're still going to take it, then we'll do the notes afterwards, because I think you already know how this is going to go. If I add a stress of adding NO2, and when I have a stress of adding something, it's an immediate change to that chemical. So I am upping NO2. Now what's going to happen is that the equilibrium is going to shift to the right to bring NO2 down, to reverse what I did with the stress. So I've increased NO2, and now what's going to happen is it's going to shift down, right? It's going to bring NO2 down by shifting to the right. So what will that do to H2O? Well, if H2O had a concentration, which it doesn't really make sense here because it is the only liquid. So I'm just going to keep on drawing that as a straight line. Doesn't even make sense if it's on the graph. For HNO3, it would increase, right? It's coming up, and I did really poorly with that line. It's tough to do it on a computer like this as opposed to a smartboard. But the NO2 is going to increase because I'm shifting towards the HNO3. Sorry, I misspoke. The HNO3 is going to increase. And then NO gas is also going to increase, okay, because it is going towards NO as well. So that is also going up. So NO2 after the stress is going to go down, and then HNO3 goes up, and then NO gas goes up. Ideally, when I draw this, I want this change to be times 2 of what this change is. Because of the fact that I have a 2 on this, right, and only a 1 as a coefficient on here. And in the same way, I want this decrease from the stress to where it went to be like 3 times this one. So looking at the coefficients and considering them is important. But when I look at concentration, what I'm doing is once I have the stress, I am shifting in the direction that will reverse what the stress was. So if I'm upping concentration, it's going to shift away from that chemical to bring the concentration back down. If I'm lowering concentration of something, it's going to shift in the direction that would bring that concentration back up. So what would the system want to do to oppose this change? Well, if I am adding more NO2, it wants to bring it back down. So bring NO2 down. What direction would the equilibrium shift in order to do that? Well, it shifts to the right because the right direction is changing NO2 to HNO3 and NO. So that's what it's doing. What would then happen to the concentration of H2O, HNO3, and NO gas because of the stress? I don't like discussing H2O because of the fact that it's a liquid. It would not be included in the equilibrium expression. So we're just going to say no to that entirely. For HNO3 and NO, those are both going to increase as I shift to the right. So this is going to go up, and this is going to go up as well. By the way, this is in your workbook, so you can take a look and kind of go through it and, do it with me. On Edpuzzle, you would have already seen these questions appearing in the stuff in the workbook. So how do you know that the system has opposed the change and is back at equilibrium? Well, after this, what would happen is if I take a look, now it would stay constant after that point. So it would be staying just solid after that, getting a flat line, which means that I now have equilibrium established again after the stress that occurred. Okay, so how would it be? It would have horizontal concentrations, or let's just say concentrations staying constant. So concentrations are constant. What happens to the Kc value? It stays the same. The Kc value through all of this is not going to be changing, but it's going to be staying constant as well. All right, another chemical reaction. And what I want to do first is kind of go ahead and maybe just go a little bit to, oh, I don't even have notes for concentration. Never mind. I lost a slide somehow. All right, so if we want to increase the maximum yield of Freon, I want to make as much as possible of this. What are 4 stresses that we could apply to the chemical system to make that happen? So first thing to figure out is, what do I want for a shift? Well, I want there to be a right shift in order to make more Freon. I want to shift towards the products. So now what stresses will accomplish that for me? Well, the stresses that I could have is I could increase HF, causing a right shift. I could increase CCl4. Nope, never mind. That won't work because it's the only liquid. I could decrease the Freon. Now that seems weird because I want to make more Freon, but what I'm doing is I'm removing it, collecting it, harvesting it, so that more will form. And then the other thing is I can bring down HCl, and again, it's going to shift towards HCl once I remove some of it to bring HCl back up. The very last thing I can do is lower energy, and that would cause a right shift, which means I can decrease temperature. So I can add HF, I can remove CCl2F2 gas, I could remove HCl gas, and I could lower temperature. When I lower temperature again, I'm doing that for the full system, right? So I'm not able to just lower temperature of one thing. This is all together in the same vessel, in the same closed system. So all I'm doing is I'm lowering the temperature of the full thing, which would cause a right shift, making more freon. So concentration summary, when I lower concentration of something, so lower concentration of chemical, it shifts towards chemical. And then in the same way, if I raise concentration of a chemical, it shifts away. So it shifts in the opposite direction, because it tries to get rid of the chemical that I added. So it tries to lower what I increased the concentration of. Last change that we can make is dealing with pressure. Now for pressure, first we have to kind of think about Chem 20 and what you learned about pressure and volume and that relationship, and essentially Boyle's law, which is an inverse relationship. If I increase the volume of a reaction vessel, then that means I'm decreasing pressure. And if I decrease volume of the reaction vessel, then that means that I'm increasing the pressure, again, because I have an inverse relationship. When I deal with Boyle's law, this is only something that's going to impact equilibriums that have gases in the system, right? Because otherwise the pressure change doesn't matter. It's not going to impact anything. But when I have gases in an equilibrium system, I can use volume as well in order to influence pressure, which then causes shifts. Now, only pressure changes that are a result of manipulating volume count for this. If I add an inert gas, for example, that doesn't actually shift anything. Would it bring up pressure? Sure it would, but it doesn't change the volume. So as a result, it doesn't have any impact. Okay, so only consider gases in this, and what you do is you compare the total moles of reactants compared to the total moles of products. And then the guiding principle is still the same. If you're increasing pressure, the equilibrium is going to shift in the direction that brings pressure back down, right? If you're lowering pressure, it's going to shift in the direction that brings pressure back up. So the equilibrium, again, is going to do the opposite of what you are trying to do. But again, only volume changes that make pressure changes count. Other changes aren't going to matter. So let's take a look at this equilibrium. Here I have 2 SO2 gas and O2 gas making 2 SO3 gas. So I have, in terms of moles of gas and reactants, 3 moles of gases. Well, in the products, I have 2 moles. So if I increase the pressure in this system, what would be the system, or what would the system want to do to oppose a change? So I increase pressure, what direction will bring it back down? Well, to bring it back down, it shifts in the direction that has less moles of gas, because that would then cause pressure to decrease. It's converting 3 molecules into 2 molecules, so you can think about it as the reaction vessel is getting less crowded. So it would shift right in order to oppose that change, which means I would have less SO2, less O2, and I would be getting more of the SO3. So rules: shifts to the side with more gas particles when pressure is decreased. It shifts to the side with less gas particles when pressure is increased. And if gas particles are equal on reactants and products, pressure will have no effect. How do catalysts affect equilibrium? They just don't. Catalysts have no impact. Okay? No shift, no impact. They do nothing. This is something that's asked quite often, and yeah, it just doesn't cause anything to happen at all. Will it reach equilibrium faster? Sure, but it won't actually impact the equilibrium in terms of where it lies. It's not a stress that causes a shift. It's not a stress at all. All right, so let's take a look at a full equilibrium here and try to figure out what we could do in terms of concentrations, volumes, everything else. So if we wanted to produce a maximum yield of chlorine gas, we want to get as much of this guy as possible. How could we change the volume of the container? What could we do to the concentration of species in the system? And what could we do to the temperature of the system in the end? So try to take a look and figure out all the stresses that would cause a maximum yield of Cl2. And here we go. What we could do to the volume of the container. I have 1 mole of gas here, while in products I have 2 moles of gas. So if I want to increase the Cl2 amount, I want to lower pressure so it shifts to the right to bring pressure back up. So how do I lower pressure? I increase volume. Okay, so if I increase volume, I lower pressure, which causes it to shift to the right to bring pressure back up. What could we do to the concentration of species in the system? Well, I can up PCl5, because that will result in a rate shift. I can lower PCl3. And I can also lower or collect out Cl2, and then we'll make more in order to bring it back up again. Last thing, what can I do to the temperature of this system in order for us to increase Cl2 yield? I would want to increase temperature. By increasing the temperature, I cause a right shift, which is the endothermic reaction direction, which will use up the heat. So by shifting to the right, it's going to bring temperature back down. Okay, another one, and this is different in that it is asking what will happen for each stress, which way it will shift. So these are the two kind of questions you can get. One is like, hey, we're trying to cause this shift. What are the stresses that will cause it? And then here I'm presenting the stresses, and you're trying to predict the shift that will take place. So I have C2H4, 2 of them, plus 2O3 gas makes 4CH2O gas, and O2 gas, and heat. So state the direction of the equilibrium shift for each of the following stresses. All right, C2H4 increases. I'm bringing this up. It's going to be a right shift. So that will be a right shift in order to bring it back down. O3 gas increases, so I am going to now take this and increase the O3 gas. That's also going to cause a right shift to use up the O3 gas and shift it to the right. Now let's say I have O2 gas decreasing. Well, that's also going to be a right shift in order to bring O2 gas right back up. Temperature increases, so I'm now going to increase the temperature, which is right here. It's on the right-hand side. Well, then it's going to shift left. That's a horrible arrow in order to bring the temperature back down. Again, take a look. This is a takeoff, right? It's going up and then away over the arrows. Pressure decreases. This one gets a little bit trickier. On this side, I have a total of 4 moles of gas. Well, on this side, I have 4 plus 1 is 5. So if I decrease volume, I am upping pressure. So then it's going to shift to the left. Oh, I switched questions there. My bad. Pressure decreases. So pressure decreasing means that it's going to shift in the direction that causes pressure to go back up again, which will be to the right. Volume decreases. It's going to shift, because this is causing an increase in pressure, to the left to bring pressure back down again. And finally, addition of a catalyst, the trick question. This does nothing, no shift. One thing I should have mentioned for gases, if moles of gas is the same on both sides, then there's no impact. I can't cause a shift with volume then because it wouldn't change the pressure, right? So if the number of moles on both sides for gases is the same, I cannot use volume and pressure to cause an equilibrium shift. Okay, very last thing is graphing equilibrium shifts. The chemical engineer can make changes and then it actually can be seen on the graphs. So when I look at a graph, here are the different changes and how they would look. If I remove or add species, you see a very sharp change for just one chemical, okay, which means that that is the thing that I stressed, right? That is the shift or the stress that I I made was removing that chemical. So if you see a very quick change for one chemical, a very quick like boom, straight up, or a very quick, it's kind of here at equilibrium, and then boom, a drastic shift down, and then it goes back up again. That is due to removing or adding a chemical. If I change the temperature, you're going to see a gradual shift for all chemicals. And then if I change the volume, you're going to see a sudden change for all chemicals as I change the volume, because all the concentrations are going to change instantaneously at one time because of the fact that I am changing concentration if I change volume, and this a sharp sudden change for all chemicals in the same direction. That is also kind of interesting, that everything will change in the same direction. So we're going to see some examples of this so you can actually tell what's happening. Like I mentioned when we looked at the previous graph, when I take a look at how things will change, we also should consider the fact that we have coefficients, so things will change more than others. So if I'm shifting to the right, H2 will have 3 times the change in concentration that CO gas would have, because I have 3 for a coefficient instead of just 1. So if I take a look at this system, for example, and I'm looking at what happened at different points, so here's point 1 and here's point 2, and what shifts took place, so what actually happened. Well, at point 1, I had an increase in H2 gas concentration. So the stress that happens right here is I increased H2 gas. And then as a result, it shifts to the left as it tries to bring H2 gas back down, right? CH4 goes up because it's a reactant that's shifting in that direction. CO gas as a product goes down because it's shifting away from it. And H2O gas is going up as well. So this stress was an H2 gas increase. Now on this stress, I'm seeing everything change very gradually as a result. So this is a temperature shift because it's a gradual, not a sharp change to everything. And then if I take a look at what happened, it's shifting towards H2O gas, right? Shifting away from CO gas. So this is a left shift as well. So how do I cause that? By cooling it down. So this was a temperature decrease shift, which causes a left a temperature decrease stress, which caused a left shift. All right, here's another question where I have Cl2 gas, PCl3, and PCl5. So first question is, in this equilibrium system representing the diagram above, equilibrium was initially established at blank, and the stress applied to the system at 14.0 minutes was blank in temperature, so increase or decrease. So if I take a look, equilibrium was originally established, I would say right around like here-ish. So as a simple answer, we could put 5.0 minutes, right? At 5 minutes, equilibrium was established. I can tell because the concentrations were staying constant. And then when I take a look at the stress, which happened at 14.0, well, at this point, I can see that this went down, and this went up. So PCl5 was increasing. So that means I must have had a decrease in temperature, a cooling down, right, which caused then a left shift in the exothermic direction to bring temperature back up. All right, one more. Actually, I think there's 2 more. So here's another one. Which of the following stresses represent the change in equilibrium at time x on the graph above? So what was done based on what we're seeing for all of these different chemicals? And the fact, again, that we're seeing a kind of gradual shift for everything means that we had a temperature change. If everything changed all at once in one direction, I could think of volume, but that's not happening here. F2 gas is going down. OF2 is going up, so this is a right shift, which means that I increased temperature. So the answer on this one is C. Really like this question, but the image is very horrible. What this is asking is what the shift is at time W, X, Y, and Z by looking at the shape of stuff. So I'll kind of read out the options, and this was a numeric response. So the stresses I could have was addition of heat. Number 2 is addition of neon while a constant volume is maintained. Addition 3 is addition of hydrogen. And stress 4 is pressure increased by decreasing the volume. So those are all the different stresses, and we have to figure out which one is W, X, Y, and Z. Okay, so for W, this was a increase to H2. I can see a sharp rise in H2 right off the bat. So this is 3 For X, nothing changed. So this is addition of neon while a constant volume is maintained. Because when I add an inert gas, it doesn't cause a shift if the volume hasn't changed. So that doesn't do anything. For Y, I can see a dramatic increase in everything right off the bat. So this is decreasing the volume. I have changed the concentration of everything to up based on the volume decrease. And then finally for Z, I can see a gradual shift of stuff. So this is going to be addition of heat, right? Based on the fact that everything is changing gradually. It wasn't a sharp change in anything. So I know that that's a temperature change. And not everything is going in the same direction as well. So I also know because of that, that has to be a temperature change and not a volume change. All right, that was a big lesson for Le Chatelier. Hopefully that makes sense. Going through the work should help as well. All right, that's it. Have a good rest of your day.